At some point, you may have come across the mathematical notation that looks like this. This is called sigma notation or summation notation. Sigma notation is a concise notation for representing sums. Often, in mathematics, a problem can involve sums with many terms that are part of a pattern. For example, adding all the numbers from 1 to 100, 1 plus 2 plus 3 plus 4 plus 5, and so on, all the way to 100 would be quite tedious to write out in its entirety. Sigma notation provides a way to simplify this process. A sum written using sigma notation will look like this. This would be read aloud, the sum as I goes from 1 to n of a sub I. Let's talk about what each part means. First, I is known as the index of summation. An I is usually used for the index, although j and k are also common variables that are used for the index. Any variable can be used as the index of summation. The index of summation will be set equal to a number. Here it's set equal to 1. This number is called the lower bound or the starting point of the summation. You can think of it as where the sum begins. It is usually 0 or 1, but it can be any integer. In addition to being called the summation's lower bound, it is sometimes referred to as the lower limit or starting index. The upper bound of the summation is written above the sigma. Like the lower bound, the upper bound will be an integer, and it must be greater than or equal to the lower bound. To the right of the sigma will be some expression, usually in terms of I, that will be summed based on the lower and upper bounds. Let's look at two basic examples. I think you will see that sigma notation is not so difficult after we do. First, let's talk about the sum as I goes from 1 to 7 of I. This sum has a lower bound of 1 and an upper bound of 7. This means there will be 7 terms in the sum. There will be 7 terms that are added together in this sum. In this sum, the lower bound is 1, so the sum begins with I having a value of 1. So in this sum, the first term, I's value will be 1. Then, the second term, I will have a value of 2. In the third term of the sum, I has a value of 3, and so on. What I have listed here is a sum from 1 to 7, 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7. Sigma notation allows you to represent this sum in a concise, simpler form. It represents and means the same thing as 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7. Let's look at another simple example. Here is the sum as I goes from 0 to 5 of I squared. Writing out this as a list of terms added together, we'll go from 0 to 5. Now that means that there will actually be 6 terms here. In the first term, I will be equal to 0. The second term, I is 1. The third term, I would be 2. And we would go the whole way up to 5, which is the upper bound of this summation. And all of these terms would be added together. In the first term, when I is 0, because the expression that's being summed here as I squared would be 0 squared. The second term would be 1 squared, 2 squared, 3 squared, 4 squared, and 5 squared would finish this sum. Again, sigma notation provides a concise way to represent what would be sometimes a long sum to write out without sigma notation. Next, we will take a look at two examples where you are given a sum that is written in sigma notation and you will be asked to write the terms in the sum. First, consider the sum as I goes from 1 to 5 of I to the third plus 2. This sum is written in sigma notation. Let's write out the terms that are represented by this sum. First, this sum goes from 1 to 5. That means that there will be 5 terms in the sum. In the first term, I will be 1. In the second term, I will be 2. In the third term, 3, then 4, then 5. These are the 4 terms in the sum that will be added together. In the first term, I will have a value of 1, and that means that the expression I to the third plus 2 would be 1 to the third plus 2. In the second term, I has a value of 2. So instead of 1 to the third plus 2, we'll be looking at 2 to the third plus 2. In the third term, when I is 3, we'll be dealing with 3 to the third plus 2. Notice the only thing that changes is the value of I. The constant plus 2 is the same as we go through the list of terms in the sum. When I is 4, 4 to the third plus 2. And in the final term, when I is equal to 5, we'll be looking at 5 to the third plus 2. The sum, as I goes from 1 to 5 of I to the third plus 2, really means this list of terms that I have circled on the screen. Next, let's consider the sum as I goes from 4 to 10 of 2i minus I squared. Here, the sum is going from 4 to 10. There will be 7 terms in this sum, starting at 4 and ending at 10. In the first term, I will have a value of 4. So 2i minus I squared would be 2 times 4 minus 4 squared. In the second term of the sum, I is 5. So you would be looking at 2 times 5 minus 5 to the second power. In the third term, I is equal to 6. 2 times 6 minus 6 squared. The fourth term is 2 times 7 minus 7 squared. Again, I'm just replacing the value of I. I'm replacing I with values incremented starting at 4. I will eventually end at 10 in this sum. When I equals 8, 2 times 8 minus 8 squared. When I is 9, 2 times 9 minus 9 squared. And finally, when I equals 10, the expression is 2 times 10 minus 10 squared. You can see that writing this sum in sigma notation is a far simpler form of the sum than writing out each term individually. But it is important for you to know what sigma notation represents. Sigma notation represents a sometimes very long sum that is most easily written using sigma notation. Now that you have an idea of the kinds of sums that are represented by sigma notation, let's go the other way. Let's take a look at a sum and write it using sigma notation. Here I have a sum that involves a radical of a few terms beginning with 1 times the square root of 1 plus 1, and then 2 times the square root of 1 plus 2, 3 times the square root of 1 plus 3. Then there's a dot, 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 which means that this sum continues in this pattern and ends with the last 2 terms that you see on the screen now. To write this using sigma notation, there's a few things we have to identify. The lower bound, the upper bound, and the expression that is being summed. When I take a look at this sum, I can see that there's one part that is constant throughout the sum. Under the radical, there's a value of 1 as the first term inside the radical. There's a value, there's a number in front of the radical as well, but that changes as you move through the sum. There's going to be a value and then a radical, and inside the radical, there's always a value of 1. That's added to another value that increases as you move through the sum, And it's important to realize that that value, that second term inside the radical, is identical to the factor that the radical is being multiplied by in each term. That number that shows up on the outside and as the second term inside the radical starts at 1 rather, and is increasing by 1 as you work your way through the sum. It starts at 1. That's the lower bound of this summation. It increases to 2, then 3, then there's a dot, 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 which indicates it continues in that pattern, 4, 5, 6, 7. And look at the last two values, 16 and then 17. 17 is the upper bound of the sum. This is a sum from I equals 1 to 17 of, now let's think about the expression. Outside of the radical, these values are starting at 1 and increasing the whole way to 17. I goes from 1 to 17. Additionally, inside the radical, the second term in the radical starts at 1, and just like the factor outside the radical, increases by 1 until it ends up at 17. The sum represented by these terms is the sum as I goes from 1 to 17 of I times the square root of 1 plus I. Let's finish with one final example of writing a sum using sigma notation. In this example, the sum involves fractions. The first term in the sum is 2 over 3 times 0 squared, then 2 over 3 times 1 squared, 2 over 3 times 2 squared. Perhaps you can see the pattern already. The sum ends with 2 over 3 times 32 squared plus 2 over 3 times 33 squared. Writing out this sum in its entirety would take a while. There would be a total of 34 terms in this sum. We can write this in a quick, concise way using sigma notation. Taking a look at the terms in this sum, I can see that each term is a fraction. Each term is a fraction. There is, in the numerator, a 2. That does not change as you work through the sum. The first term has a 2 in the numerator, the last term has a 2 in the numerator, as do every term in between. There are 2 factors in the denominator of each term in the sum. The first factor is a 3. In each case, the first factor is a 3. That doesn't change as you work your way through the sum. The second factor in the denominator of each term does change. The first term has a 0 to the second power, then a 1, then a 2, then a 3. This sum begins at 0, begins with this number, this factor in the denominator being 0, works its way up by 1 to 33. The lower bound of this summation is 0. The upper bound of the summation is 33. In the denominator of the sum, the 3 is being multiplied by what I will call I, a factor that starts at 0 and in this sum ends with a value of 33. The sum on the screen, 2 over 3 times 0 squared plus 2 over 3 times 1 squared, going the whole way up to 2 times 3 over 3 times 33 squared, can be represented using sigma notation as the sum from I equals 0 to 33 of 2 over 3 times I to the second power.